If I have a sample x1 through xn and I have a statistical model with an unknown parameter theta, then statistics is all about drawing inference about this theta based on my sample, so I can create an estimator of theta, which is a statistic, that is, it's a function of the sample. Just because I create an estimator of an unknown parameter doesn't mean that it's a good estimator. I want my estimator to use the sample efficiently and return a number as close as theta as possible. This is why we need methods to evaluate estimators, and one of the methods that we use is to check if the estimator is unbiased. If it's unbiased, then that is good news. That's sort of a thumbs up for the estimator. However, it turns out that in many cases, I can actually find many unbiased estimators for the same unknown parameter. And in this case, I need a method to distinguish between these estimators in order for me to pick one of them, which I will then use to make inference about theta. So let's say that we have two unbiased estimators. It could be more, but let's start with two, theta 1 hat and theta 2 hat. They are both unbiased, so the expected value of theta 1 hat is theta and the expected value of theta 2 hat is theta. Let's say that this is the PDF of theta 1 hat. It's unbiased, so its expected value is equal to theta. If we play this game repeatedly, then this density will approximate a histogram of my guesses of theta. Let's say that the density of theta 2 looks something like this. It too has an expected value of theta, and we have to decide whether we want to use theta 1 hat or theta 2 hat as our estimator of theta, in this case that they are both unbiased. If you look at the PDFs, then there's approximately 95% probability that theta 1 hat will give me an estimator in this interval. That is, I'm assuming that this area here is 95% of the total area under the PDF. If I create the same interval for theta 2 hat, it will come out to be a much wider interval, since theta 2 hat has a much higher variance. So even though they're both unbiased, it's pretty clear that we should select theta 1 hat as our estimator. It will, in most cases, return an estimate that is closer to theta than will theta 2 hat. We cannot, of course, say for sure that this will happen. Theta 1 hat may be very unlucky and return an estimate way out in the tails of its PDF, while theta 2 hat may be very lucky and return an estimate very close to the expected value theta. But probability-wise, we are better off using theta 1 hat as our estimator. We need some terminology for this effect, and the terminology we use is efficient. We say that theta 1 hat is more efficient than theta 2 hat if the variance of theta 1 hat is less than or equal to the variance of theta 2 hat. We only do efficiency statements between estimators that are unbiased. We can also say that an estimator is efficient, full stop, without comparing it to any other estimator if it is the case that it has a smaller variance than any other unbiased estimator. Here is a simple, although slightly silly example. I have a sample, I assume it's a random sample, and each observation is drawn from a normal distribution. I know that the sample mean is unbiased, but so is this estimator, x bar n half. X bar n half is simply the average of the first half of the sample. I sum the first half of the sample and divide by half of the sample size. So I have two unbiased estimators, X bar and X bar n half, and we can compare them based on the efficiency measure. So to do that, we figure out the variance of each of them. We know that the variance of the sample mean under the random sample assumption is sigma square over n. Using the same method, we can also show that the variance of the second estimator, which uses only the first half of the sample, is sigma square over n half, which is the same as 2 times sigma square over n. So even though these are two unbiased estimators, we would always pick this one over this one because it has a lower variance. It is more efficient.